Hi madam, this is a group assignment presentation for course DME 4093 Advanced Topic in Software Engineering. I am Xianiming Matrix number 67645 from Group 28. Introduction. According to her and others, they have studied about the multi-tier fog computing model with large-scale data analytics service and proposed a new multi-tier fog computing model for smart cities application, which has well-defined functional model that can minimize the potential problem of dedicated computing infrastructure and slow response in cloud computing. Furthermore, according to Edu and others, the traditional method to implement IoT application has become unsustainable due to the impact of latency, network congestion, storage costs, and privacy. The study has proposed a solution on how to split the IoT application among the edge and cloud resources to improve the performance of response time, bandwidth consumption, and edge-to-cloud and cloud-to-edge messaging costs. Arnawa and others have summarized the fog challenges per opportunity in the context of big IoT data analytics on fog networking and explain how massive IoT data analytics can propel the Internet of IoT for industry to grow. Although the cloud structure is powerful, but it is not suitable for facilitating time-critical or inability to operate in place with poor internet. Review on proposed methodology. Her and others has presented fog functional model to illustrate the functionality of fog nodes, which are fog master and fog worker. Benchmarking experiments is done on Raspberry Pi computer with Spark computing engine to measure and model the workload for various analytic activity over multi-fogs. Besides, Edu and others propose a programming model that have the ability for the developer to define how to automatically split the data flow across the edge and cloud by specifying a set of data flow constraints. The technique or method is based on RParser, which is a programming system that is already exists. A case study about observe, orient, decide, add loop is carried out, which refers to the decision-making cycle of observe, orient, decide, and add. Arnawa and others do survey and observe for the IoT data analytics with fog computing and focuses on enhanced programming model and application for better and reliable deployment of fog computing structure. In addition, the use cases are studied to better understanding the emerging era of fog.
Good morning, madam. My name is Ko Sing and my matrix number is 66399. Today, I will continue to present my parts for the discussion. Fog computing. From the writer points of view, the findings gathered from the different research shown that for fog computing as a distributed and hierarchical framework with scheduled storage, virtual machine image, embedded virtual cache, and transient storage and network resource deployment with the addition of CC functionality at the edge of IoT. This work exemplifies some key characteristics as well as enduring general ideas about potential challenges, such as how fog computing can expand CC service at the edge. As a result, it is clarifying some use cases that prompt the needs for fog computing, particularly the importance of real-life data analysis for IoT, typically in healthcare, STLS, and smart grid. Their research focused on fog consequence and disruption in three key areas: IoT, big data analytics, and storage. In the sense of analysis, the multi-tier fog computing with large-scale IoT data analytics for smart cities, we can see that large-scale analytics service using fog computing are feasible. When the analytics job arrival rate is low, a fog phone with opportunities distributed computing resource can provide good analytics service quality on their own. With the growing popularity of analytics service, more defaults with dedicated and larger pools of computing resource can be deployed to provide better analytics service. To talk, the overview of distributed operator placement IoT data analytics across edge and cloud resources. This work provides a framework for resolving the operator placement problem of Internet of Things data flows between edge and cloud resources. Using a three-phase additive WEX model, the author proposed a new operator placement strategy to reduce end-to-end latencies, data transfer rates, and messaging costs between the edge and the clouds. The results show that the system can reduce end-to-end latency by up to 45%. Furthermore, our system can reduce the data transfer rate and the number of messages sent and received. As a conclusion, the IoT data analytics in software engineering can be analytics service over fog, as well as the proposed QoS array resource management schemes were tested on various computing architectures with and without fogs. The simulation results demonstrate the effectiveness of the proposed QoS schemes and the efficiency of the analytics service model over multi-tier fogs. Besides that, despite the numerous benefits of fog computing for business continuity, efficiency, and cost reduction, there are numerous challenges to overcome during the industrial data management phase. Many studies have been conducted on IoT applications, and most of them have been linked with fog computing, primarily in developing markets such as manufacturing or oil and gas. However, many research projects that are still in the works or are uncertain about the advancement and development of smart city may be with pre-existing smart buildings, STLS, and sensor monitoring networks. Moreover, using an experimental testbed made up of edge and cloud resource that was used to deploy and execute real-world IoT applications. The operator placement approach was compared to three other strategies from the literature demonstrating the framework's ability to efficiently place computation between the network's edge and core. That's all from me. Thank you.